This is video 831, and we're looking to perform basic operations with matrices, including addition, subtraction, scalar multiplication, and basic multiplication of matrices. These operations, you do need to know how it works, because I will ask you questions that kind of show me that you understand how it works. Of course, we will use our calculator for larger calculations, okay? But we're going to be looking at very simple matrices to know what's going on in our calculator when we plug things in. So let's take a look at... Sorry. First of all, just to make sure we know notation. A capital letter such as A, B, C, or D can denote a matrix, okay? A lowercase letter in brackets can also denote a matrix. And what happens is this IJ right here is actually describing that it has rows before columns, and J columns. So when we're talking about this matrix here, A2, 3, this guy here, is referring to the second row, third column, right? And that's why it's called A2, 3. So that's important because when we show you some examples, that's the notation we're using. So use a subscript, not really to say we're timesing things by 2, 3. We're actually describing a term, a value inside of the matrix that's in row 2, position, column 3. So that's important. The second word that's going to be used a lot is order. MN means it has M rows and N columns. So it's really telling me like the dimensions of the matrix, how big it is. So if M is equal to N, of course, then it would be a square matrix because it would have equal rows and columns. So keep your eye out for those types of terminology throughout this, and of course this is all in your book, or you can review this if you couldn't remember something in the future. So let's take a look at a few definitions. You don't have to write all of this down, but it's just to clarify things. So two matrices are equal if and only if they have the same order. So they have to be the same size matrices, okay? They both have to have the same dimensions. And all the terms are equal for every row and column. Meaning, if all these two matrices are equals, they have this term that's equal. And if we want the whole matrix to be equal altogether, every single term inside would have to be equal. So for instance, y plus 1 would have to equal 5. Therefore, y would have to be 4, because 4 plus 1 is 5. So every term on the inside would have to be equal to the corresponding term in the other matrix. So when we're saying things are equal, that means that every piece of the matrix is equal to the piece in the other matrix. Matrix addition and subtraction is actually quite simple. You're going to add and subtract fairly logically. All your basic properties stay intact. So you can add in any order. That's a commutative property. You can group things and add things together on the front end and then on the back end. It doesn't matter. You can group them accordingly. The additive identity means you can add the additive identity to things and it will not change the identity, quotes there, identity of the matrix, meaning it'll stay the same if you add 0, duh, right? And last but not least, there's the additive inverse. So every operation has an inverse operation, meaning the opposite. It means it cancels it out. So meaning if I add A plus its inverse, I will get 0. And inverse in this case will be the negative of the matrix. And we will talk, it's very obvious once you know what adding is. So when we're adding these matrices that you see in this example down here, over here, we would add corresponding pieces. So 1 and negative 1 would add to give me 0. And again, 2 and negative 2 and 6 would add, and they'd stay in that same top right to give me 4. And so on. So 5 and 4 would add to give me 9. So you just add things that are in the same location. So the only time you can add matrices is if they are of the same order, and that's the only thing I didn't say yet, is that they have to be in the same order. They all have to have the same size, okay? Subtraction is also very logical. Of course, then you're just subtracting. So I don't have many examples of this because it really is that simple. The next thing that we're going to be doing, so the zero matrix is just a zero matrix with zeros in all the spots. So the order will depend on the matrix you're trying to add it to, but it's not going to change anything, right? But additive inverses, of course, everything has to be opposite. So every single term has to have its opposite additive inverse on the other matrix in order for it to be the additive inverse of the original matrix, because then it would add up to 0. So these are all very obvious things, but I just want to make them clear. Last but not least, scalar multiples. This is something that's just simple. A scalar multiple is when you take and multiply a matrix by a number. So it's like you're scaling it up, kind of like you're scaling up a triangle and making it larger. So we're scaling up the matrix, and the way we do that is we just times every single thing by that scalar multiple, 4 in this case. And so everything got 4 times larger. And every single piece, it's kind of like you have to distribute that scalar multiple to every piece on the inside. With scalar multiples, you can use associative property, distributive property, and the scalar identity property, meaning 1 times the matrix will always equal the same matrix. So all those properties re-exist for scalar multiples. Now let's take a look at a quick example. We're going to do 2a plus 3b. So it starts with, just like order of operations, you're going to start with multiplying by 2 and multiplying by 3, and then we'll add together at the end. So we're going to start by doing 2a. So 2 times the matrix A, which will give me -4, 10, 6, and -8. 2a. Then we do 3 times matrix B. So we're going to do 3 times matrix B. So we distribute the 3 to everything, and we get 18, -9, -3, and 0. Last but not least, we'll simply add things together, adding them up, adding each component. Of course, they have to be the same size in order to do this. Keep adding each corner until we get the resultant matrix, which is 14, -3, 7, -8. So fairly simple, right? These are important pieces to understanding other components and to solving systems in another way. The last thing that I want to look at with you is multiplying matrices. So this is important if we want to learn one more way to solve systems that maybe some of you will like better than reduced row echelon form. The definition of matrix multiplication is very unique and different. So let me show you a piece of that. It starts with understanding a couple of things. In order to find the resulting spots, for instance, this corner right here, that corner is in row 1, column 1. So the way we get that is we multiply things from row 1, so that's what I'm talking about, this row right here, and we multiply that by column 1 in the other matrix that we're multiplying by, because this is matrix A times matrix B here. That's what we're doing. And that's how I get the result. But notice a couple more things. We do A times E, okay, so we're doing A times E, the first two pieces, and then we're doing B times G to get and adding the results together. So it's a very odd multiplication. You don't use FOIL, but you do add things. So it's a very interesting way to multiply things. And we'll talk about why that works when we look at the systems. You'll see why we need a definition that works so we can solve other problems. So again, let's look at the next corner. The next corner would be row 1, column 2. So in order to do that one, I need to multiply things that are in row 1 with things that are in column 2 of the next matrix. So I'm going to do A times F, B times H, and add the results together. So let's see it again. Row 2, now I'm in row 2, column 1. So I'm going to do everything in row 2 times the pieces in column 1 and add the results together. So this would be a good example to jot down in your notes, just because I think it would help you kind of think about what's going on here. Here's the key. The row before the column. That's always true. When we're talking about the size of a matrix, we use row before column. When we're multiplying matrices, we're doing row times column. Everything is row by column, row, column, row, column. Keep that in mind, and you'll be more successful with these operations. Let's take a look at with a non-square matrix, okay? Because with the square matrix, everything kind of works out nice and it lands into a nice matrice. But we have a non-square matrix, so we're talking about two matrices, A and B, that are not the same size, okay? Notice their size differences. One's M by N and one's N by P, meaning they're different sizes. But here's what we need to notice about them, how they're similar. They each have an N, meaning the first matrix has N columns, and the second matrix has N rows. That always has to be the same in order to multiply two matrices. You can't multiply every matrix in the world. It has to have a commonality like that. Notice that M and P can be different, but the first matrix has to have the same columns as the second matrix has rows. That has to be the same. And if we think about why that makes sense, we'll look at that in just a second, why that makes sense. Here's the second key. The last key is that the result will be an M by P matrix, and that's because it was M rows in the first matrix and P columns in the second matrix. So let's take a look at why we have to have them be the same. So if we're looking at row I, and we're trying to find the resulting spot that's in position P, I, J. So that means, of course, that we're in row I in column J. So that means we're going to multiply row I with column J. And we have to have the same number of pieces. Now I just put random math symbols there to help you see, but we have to have the same number of pieces in order to multiply and add things together. And that's the key here. That's always how it will work. And it will land in row I, column J. So let's take a look. I think examples will make the most of this here, and you're going to give it a shot. We'll talk about it in class tomorrow as well. So here's your first example on this. We're finding the product. So let's first look at the order, the sizes of these matrices. So the first matrix is 4 by 2, row by column. Okay, row, 4 rows, 2 columns. Second matrix is 2 by 2, and we're timesing the two matrices together. Notice how those inner pieces, the row and the number of columns in matrix 1 and the number of rows in matrix 2 are equal. Those are the same. They have to be. Second thing you should notice is that the outside terms will be your resultant size. So my resulting matrix will be a 4 by 2, meaning 4 rows, 2 columns. So let's multiply this out and see what we get. So when we multiply this out, we're going to do, for the first position, we're going to do row 1 times column 1. And that's going to be -1 times 4 and 2 times -2. -1 times 4 is because those are the first two pieces, plus 2 times -2, the second two pieces. That's going to be in row 1, column 1. Now let's take it the next piece. Now we're in row 2, column 2. So we're going to go down row 2, column 1, column 1, not column 2. Again, we're going to multiply the pieces, 0 times 4 and 1 times -2. Now let's go row 3, column 1. So 3 times 4, -1 times -2 again. 3 times 4, -1, and that's how I got this. And then -1 times 2, that's how I got this. -2, of course. So keep that in mind. I'm just trying to show you how we're getting all this. And last but not least, row 4, column 1 still. So all these calculations, odds are you'll kind of do them in your head or you'll punch them into your calculator. I'm showing my work so you can follow what I would do in my head or my calculator. Now we're looking at column 2. So now we're going to look at column 2, and we'll look at all 4 rows again. So row 1, column 2. Row 1, column 2. We'll multiply the pieces and add them together. And continuing on, multiplying the pieces and adding them to now. Row 2, column 2. Row 2, column 3. Row 3, row 4, column 2. Now, what do we get for the results? Just simply do the math there. So we're just doing these basic calculations, multiplying things out and seeing what we get. Okay? That's all that it is. It's a weird operation, don't get me wrong, but once you learn it, it's not that hard. Okay? Here's your checkpoints for the video today. We'll look at this example in class tomorrow. Here's your checkpoints. Find the following matrix if possible. So I want you to multiply out A times B. Okay? So give the matrix multiplication a shot and see if you can find one of the 4 answers. The free response question is similar to that easier example. This is a scalar multiple of 3 times A by 3. Add it to B. Just try and list in your Google form what the result is. Thanks for watching. Bring those questions in with multiplying and hopefully you found success. If not, remember after the checkpoint there's a solution video where you can see how to do this before you even enter class.